based on how easy or hard they have to learn.
Yeah, thanks to the organizers for putting up a great workshop and for everyone for sticking around for the last talk of a very long week. So I'll be talking about the quantum hardness of learning, but this is, let's say, not particularly from a machine learning perspective, but a computational learning theory perspective. So we're going to be talking about a very rigorous model and then prove some lower bounds on what you can or cannot do. So let's see. I hope this works. Okay, never mind. Okay, so what is the big idea? So in 2005, Scott Aronson had one of the 10 semi-grand challenges for quantum computing, where he asked if shallow classical circuits can actually be learned quantum efficiently in the PAC learning model. So the probably approximately correct model of learning. And the one thing that we show is, unfortunately, you can't. Quantum resources are not going to give us any exponential improvement in this model. And this may seem like a contrived problem or something very theoretical, but why should it even be interesting? So there is a connection to, let's say, neural networks, because a particular class of shallow classical circuits can actually, they characterize feed-forward neural networks. So somehow we're talking about how efficiently you can learn the weights of these neural networks in this case. Of course, the one caveat is that this is a conditional result. We don't have an unconditional result to say that it's hard. So, if that condition gets broken. But I'll talk about that a little bit more later on. And finally, what we're showing is a worst case hardness result. So it's not necessary that, the whole game is over. There could be something you could still do on average and for some interesting subclass of, maybe these feed-forward neural networks or something. Okay, so the nice thing is I think this result kind of encapsulates different aspects of what's been happening over the whole week here. So the first thing, I guess, is that there is some connection to learning theory and machine learning ideas on a theoretical perspective. And that is basically the idea that we're going to need. I'll also need some ideas from circuit complexity, and Robin was very helpful in introducing some of those concepts, so it will hopefully not seem too foreign to everyone here. And the last part that I need is actually some results from post-quantum cryptography. So, if any cryptanalysts are sitting here. So we're going to connect all of these together to kind of prove our hardness result. And so let's kind of get into it. I'll basically introduce what concepts we need from each of these aspects and go forward from there. So for the quantum learning theory aspect, what we need to define is a specific model that we care about. So it's usually called the active learning model. So I have, let's say, an active learner for a specific concept class. So we're talking about classical concepts here. So it's just a Boolean function from n bits to 1 bit. And let's say I have a learner A for that. If I have access to the concept under an Oracle definition, so the Oracle OC kind of hides a particular concept, C bar. And I have to learn it under a specific distribution D, which means that essentially if I ask for give me a sample from this distribution, x1 and x2 will be distributed according to D, and I'll get the value of C bar of x1 and C bar of x2 when I ask for it. I'm also given a little more power. I'll say that there is a very specific y1 for which I want to know the value, and the Oracle will tell me what that is, and this is called making a membership query to the concept, because you're checking depending on whether the value of C bar of y is 0 or 1, it tells you the membership in this concept. After doing this, the learner is going to output a hypothesis, and we say that it has to satisfy certain conditions. It's called that being epsilon approximate, or like a very pretty good hypothesis, if for any random challenge that is distributed according to this distribution D, the fact that the hypothesis will not match my concept is very small. So think of epsilon as being 1 over poly in the number of bits. So we say that this learner is an epsilon learner for the concept under this distribution. If for every concept C in the concept class, it'll output a hypothesis that's epsilon approximate with high probability, which means over all possible concepts, you need to do pretty well. So this is slightly a special case of what the PAC learning model. So the PAC learning model, you need to satisfy that A is an epsilon learner for the concept class under every distribution D. So this is a slight restriction of it, but then we want to prove hardness, so we want to do it in a slightly weaker model. What do we care about? Of course, we care about the running time of the learner. We also care about, similarly, like how many times you're going to access the oracle, so like the sample and time complexity. Usually that's what people want. Good question to ask is, okay, in this case, so all I talked about right now was just the classical thing. So where does the quantum come into the picture? So let's say we try to make all of the examples and all of the oracle access quantized. So a quantum example essentially would just be a superposition where all the x's are kind of with amplitude square root d of x. So why is this a good thing? If you measure this sample, essentially you would get to sample an x according to the distribution d. So it's a fairly standard generalization you can care about. And if you send in a quantum query, you get back with a standard query access. So that's going to be your membership queries that you make. You can, of course, ask for things in superposition and so on. So under this model, you can ask, like, what's a good choice for D? Let's do the one thing we know how to do. Let's say D is the uniform distribution on all inputs. And that has worked well in the past because we know of efficient quantum learners under this uniform distribution, whether it's the Bernstein-Vazirani algorithm or work by Schutte and Jackson for depth 2 circuits. And they could do it essentially by using Fourier sampling. So all of these techniques, somehow you get a constant number of samples, and then you just Fourier sample and analyze it. So in most cases, that has worked. And in most of the efficient learning algorithms we have for classes of functions in this kind of a model, usually Fourier sample is always hiding in there in one form or another. OK, so much for the learning model. So what are the Boolean circuits? A very quick refresher. So we have the AND, OR, and NOT gates that were already defined previously, but there's another kind of gate that we would want, the majority gate. So we say that the majority gate outputs a 1 if and only if half of the inputs that go into it is at least 1. Okay. So then any Boolean function that goes from n bits to 1 bit is said to be computed by a shallow or constant depth circuit, if the following holds. We saw NC0 and AC0 previously. So NC0, again, you have only fan-in 2 depth circuits, and they're constant depth. And, well, polynomial fan-in, probably not, but probably should say unbounded fan-in, so sorry about that. So F will belong to AC0 if it's got unbounded fan-in and OR gates and NOT gates in there. But we also need another class. So we're going to go one step further from the previous talk. So we're going to have this class called TC0, which is also called for threshold circuits. But here you can have majority gates thrown in. So in some sense, think of majority as telling you the threshold of whether it's at least half or not. So any kind of a threshold circuit can kind of be broken down as long as you have the majority circuit. So these are the 3 classes that we care about. They are successively contained in each other. And then the question that we're asking essentially says, can we learn these concept classes, TC0, AC0, or NC0 efficiently? Right. OK. So of course, one reason to care about shallow circuits is because you have these neural networks that can be modeled in this way. So here there's no feedback or anything. They just go in one direction from the input layer to the output layer. And all of these essentially can be characterized as threshold circuits. Yes?
So when you say that there is a relation with the neural networks, why is it that you need to back-learn a neural network?
It's
distribution of the inputs and you want to learn?
Yeah, maybe there is some ideal way. So if you had some way of getting a signal for this function from, let's say, naturally, and you had those samples, maybe you can use it to kind of approximate the weights of a neural network that you want to model this concept in some sense.
OK, I'm just saying that it's probably for a fixed distribution and not learn it against all possible distributions, right?
Yeah, so the uniform learning is doing it under a sort of fixed distribution of inputs, right? Yeah, pack learning would do it against everything, sort of. Yeah. So we already know that there are separations between NC0 and AC0, and these separations have been proved in also various models like distributed computing and with some interaction thrown in and so on. So we know that shallow quantum circuits do something well, so quantum resources in a learning setting, can they be harnessed in an efficient way for us to show something non-trivial? What we know is in the classical setting, these classes are known to be hard to learn. So that's under assuming that factoring is hard. So this was a result shown by Karashnov in 1993. So of course the question is, well, factoring is not hard quantumly, so definitely that result doesn't hold. So maybe can we get an improvement? And of course, as I said before, for some smaller classes like NC0 and for depth 2 AC0 circuits, we do have efficient learners under the uniform distribution. So it's a question of asking how much can we increase the power or increase the size of what you can learn efficiently. So the last part is now pseudorandom functions. So that's what we need from the post-quantum crypto world. So for those not familiar with it, we say that a function family, so you have a collection of a keyed function. So S is kind of thought of to be the key that keys each or indexes each function in the family. And the function goes from, let's say, k bits to L bits. And we call this function family pseudorandom if the following holds. There is no efficient algorithm, in this case, what's called a distinguisher, which has access to this function as a black box and cannot distinguish whether this function actually comes from my family F or it's a uniformly random function going from k bits to L bits. And of course, you want to do this with high probability, right? So the probability that I output a 1 when the function is from my function family versus when the function is randomly output, the difference, the bias should be high. So a natural thing is you want these objects to be quantized, so you can have a quantum algorithm that has access to this function family, and you will call that it's quantum secure if even given this quantum access to the function, you cannot essentially distinguish whether F is uniformly random or not. So we take one candidate PRF and construct it. So the candidate PRF that we care was introduced by Banerjee, Paikard, and Rosen in 2012. So it's constructed using a problem called learning with rounding. And this is kind of a deterministic variant of learning with error. So you're not sampling noise again and again. And we need it over rings because we need a very efficient implementation of it so that we can actually fit it into constant depth circuits. The good thing is we know that ring LWR under certain conditions reduces, like it's at least as hard as ring LWE. And for the kind of parameters we're looking at, the best known algorithms that we have require exponential time. So that's a plus point for us. Now that we have all of these ingredients, let's see how to connect everything together. So what we want to do is, now that I'm given this PRF family, let's say, how do I, so I have the concept class that's given. What essentially do I need to do? I need to show that if I had an efficient learning algorithm for this problem, then I would be able to construct an efficient distinguisher that can basically distinguish my pseudorandom family, right? So how does it go about doing that? Well, my learner has to make queries to the concept class, but any distinguisher that I construct has access to the concept class. So somehow, any query that the learner makes, my distinguisher will give the answers required for it. Right? So if I ask for a sample, it's going to access the unknown function and then give the required sample. And anytime I ask for a specific query, it's going to do the same thing. At the end of the day, the learner is going to give me a hypothesis, and this is actually a classical hypothesis that we care about. And we'll say that the distinguisher is going to output a 1 if and only if my learner outputs. The hypothesis evaluates to a 1. And what we show using quantum information theoretic arguments is that if my learner outputs a pretty good approximation of this unknown concept, so half plus beta approximation, then basically what my distinguisher can do is actually can identify my fake random function with half plus beta over 2 probability. So somehow now you've constructed a distinguisher that can basically tell you what's happening, because you can essentially learn the function that's being hidden. So essentially, if beta is at least 1 over poly of n, then your game is over. But of course, it matters that you have to choose a pseudorandom function that's actually quantum secure. For instance, factoring does not work anymore. And the last step actually has to do with showing that these PRFs, the instances that we care about, can be computed in TC0 or AC0. So for the first step, that means we have to literally go into the ring arithmetic and so on and figure out exactly what kind of circuits are constructed. You need to sort of play with the parameters to make it fit into the right size of the circuit. But once you can do all of that and put it together, what you essentially show is that if we think of ring LWE as being super hard for quantum computers, then we have shown the existence of some concept classes that cannot be learned efficiently in this model of computing. So that's basically how the proof goes. Well, at the end of the day, all of this just seems like a lot of things that are going on, and you just say, okay, just tell me what's the main idea. This summarizes all of our results. So there are two. The second result is something that on the last line is something I didn't talk about, but that also works for the PAC model. The crypto primitive that we use there is public key encryption system, which is based on LWE. And I think the idea there is that somehow the decryption function in that case can be computed in a TC0 circuit of depth 2. So if we try to use the same techniques and make it all go through, then even in a distribution-free PAC model, so basically under any distribution of inputs that you get, you can't do anything to learn it, assuming that LWE cannot be solved in BQP. But the first result that you have says that essentially, if ring LWE cannot be solved in polynomial time, then you have something for TC0 where you can't have a polynomial time learner. The second line is interesting because this kind of a result is actually not known in the classical setting. Somehow the way the parameters play around with in the classical proof, if you try to have a distinguisher that runs in super polynomial time classically, then you don't get a learner that distinguishes very well for factoring. So you somehow can't get these parameters to work in the classical setting. So somehow you need the quantum proof to make it go through. And you also get a super polynomial time lower bound, which says that for some constant, there is no n to the O of log nu to the n algorithm for AC0. This sort of matches the upper bound that is known classically for solving AC0 circuits by Linil, Mansoor, and Hassan. So we're sort of getting tight bound. So of course, we had some cryptanalysts sitting here earlier this week. What if they actually managed to solve and break LWE? There are some other candidates that we can look for, except that they are not computable in very short constant depth circuits. So we can still get some hardness results for logarithmic depth circuits, but not for constant depth anymore. So if anyone wants to come up with other primitives that can be computed in constant depth, we're all for that. What are some open questions? Some specific things that are of interest is that we know that depth 2 AC0 circuits can be solved efficiently. These are just and or trees. But classically, we know that depth 5 AC0 circuits cannot be solved efficiently. Quantumly, we don't know exactly what is the depth at which it starts getting hard. We just know that there is some constant for which it's hard. So, if someone wants to dig in and figure that out, that is an interesting thing to understand. Again, whether there are some techniques that you can use for let's say a subclass of these feed-forward networks, because we show that some cases it doesn't work, but that doesn't necessarily have to hold for everything. And I guess the next thing is, what can you talk about the learnability of quantum circuits or states? I guess there are some things known about the sample efficiency of these things, where it's known. There's recent results by Ling and Chung in Chung and Lin in 2018, where they talked about requiring only a polynomial number of samples to efficiently learn polynomial size circuits. But then, yeah, whether you can do it time efficiently is still a question that's interesting. And yeah, what can you do for things like QNC0, which show exponential advantage to things change? So yeah, with that, I will conclude. Thanks for your attention, and thanks for sticking around.
Thank you, Aarthi. Yes.
So it seemed that it was important that the distribution D was uniform.
Yes.
Right? So, it seems that it's important that it's at least efficiently sampleable in order for the reduction to go through from sort of learning to breaking the PRF property, right? Because you would have to sample the superposition over the
Yes, yes. That is sort of required. Well, for the distribution-free pack, you sort of have a way of, I mean, you're doing that against all distributions as well. But the thing is, yeah, you can kind of do enough of a sample so that it looks uniform enough for you to go through and prove your hardness result. So yeah, there's a reason you wanted, for a hardness result, it's enough that you prove it just against uniform distribution. But yes, you need a distribution that can be efficiently sampled. Otherwise, you won't be able to create the stuff that you need.
Okay, so before, together with Thinking Aarthi, I want to thank the Simons Institute for hosting us here. I hope you all had a good time. I want to thank you all for staying. We had some very interesting discussions. I hope you enjoyed them. I want to thank all the speakers for giving the talks, and especially the people who took part in the open and not on the mic kind of discussions. I hope you had an interesting understanding of all the prospects and challenges, and come back to Simons. There are more workshops this semester, and yeah, so let's thank Aarthi and all the speakers again.